All right, we're going to go through the assembly line balancing quiz exam from Chapter 8. And we see the text of the question reads, an assembly line with 28 operations is to be balanced. The total amount of time required for all 28 operations is 39 minutes. The longest operation takes 2.2 minutes and the shortest 0.8 minutes. The line will operate for 450 minutes per day. Questions number 1 and question number 2, what is the minimum and maximum cycle time? Both of these questions can be referenced back to page 154 of the text. I'm going to flip to that to a slide that shows that here, and we can see that in the middle of page 154, cycle time cannot be smaller than the largest operation time, nor be larger than the sum of all operation times. So when we go back and take a look at our examples, cycle time cannot be any shorter than the longest operation time, and it can't be longer than the sum of all tasks. So for question number 1, the minimum cycle time is 2.2 minutes, and the maximum cycle time is 39 minutes. Okay, so again, that's here on page 154. Let's go on to question number 3. What is the theoretical maximum output rate that this assembly line can achieve? Well, we didn't really see maximum output or that output formula in the text, but if we go back to page 154 and take a look at our cycle time, cycle time is looking at the allowed amount of time, this A, divided by output. So our available time divided by output. So when we look at this formula, cycle time equals available divided by output, we can solve this equation for R, or output, by multiplying both sides of the equation by R. Over here on the left hand side, we know that we can cancel out these R's, and on the left hand side of the equation we need to isolate R by dividing by cycle time. So we'll divide both sides of the equation by cycle time, and we end up with this equation that output equals the available time divided by cycle time. So let's look at the theoretical maximum output rate that this assembly line can achieve using that equation. So output equals available time divided by cycle time, and we know that our available time is 450 minutes per day. And we're going to divide that by our cycle time, and in order to maximize our output, on the left hand side of the equation, the only way to make that R big is by dividing by the smallest number possible. So if we want the smallest number possible in our denominator, we need the minimum cycle time. We've already determined that the minimum cycle time is 2.2 minutes per day. So we know that our output is going to equal 450 divided by 2.2, or 204.5 units per day. So our maximum is this 204 units per day. Let's move on to question number 4. What would be the minimum number of workstations necessary to reach the theoretical maximum output rate for this assembly line? Well, we remember that our number of workstations equals the sum of our tasks divided by cycle time. And we know in our problem that we have the sum of our tasks is 39 minutes, and our cycle time is 2.2 minutes. So the number of workstations necessary is equal to 17.7. Now, we also know that we can't have a partial workstation. So anytime there's a fraction of a workstation, even if it's 0.1, we know that it exceeds the full range of 17 workstations. So we need to round our workstations up to the closest or to the next integer, which would be 18 workstations. So 18 workstations is our answer for that problem number 4. Moving on to problem number 5. How efficient would this assembly line be if the order of precedence allowed the operations to be grouped into the minimum number of workstations necessary to reach the maximum output rate for this assembly line? Well, we know our efficiency equation equals the sum of our task times divided by the number of workstations times cycle time. So how efficient would this assembly line be if it grouped into the minimum number of workstations? So we're going to use the minimum number of workstations from our previous answer was 18, and we knew our cycle time was 2.2, and in the numerator the sum of our task times was 39. So we have this equation that efficiency equals 39 divided by 18 times 2.2. So 39 divided by 18 times 2.2. So we end up with 39 divided by 39.6, and so our efficiency equals 98.48, or 98.5 rounded up percent efficiency. Okay, let's move along to question number 6. This assembly line cannot achieve the minimum cycle time, and the current order of precedence has the operations grouped into 9 workstations, and the current cycle time is 5 minutes. What is the efficiency of this assembly line? So we're going to have to use 9 workstations and a cycle time of 5 minutes. Let's go to a fresh piece of paper. Our efficiency equals sum of tasks divided by number of workstations times our cycle time. So efficiency equals 39 divided by 9 workstations and a 5-minute cycle time. 39 divided by 45, and we end up with 86.67% efficiency. Moving on to number 7. What is the maximum efficiency of this assembly line with a cycle time of 5 minutes? Well, we know that if we go back and look at this 86.67%, that's not very efficient. And well, we know that perhaps 9 workstations isn't as efficient as we could make it. So the question that's asking us here is, what's the maximum efficiency? How can we maximize the efficiency of this assembly line with a cycle time of 5 minutes? So we're going to take our equation of our tasks. So our sum of task times divided by number of workstations times our cycle time. In order to maximize efficiency, we need to minimize our workstations. So we know that our sum of our task times is 39, and if n, or the number of workstations we need, is 39 divided by our cycle time of 5 minutes, we know that the most efficient number of workstations that we can get is 7.8, or got to round up to the most to the next integer, so we can use 8 as our number of workstations. So back to our equation here, we know that 8 is going to have to go in there, and our cycle time is going to be 5, and we've got 39 minutes in our numerator. So 39 divided by 8 times 5 is 40. Our efficiency is 97.5% efficient. That's the maximum efficiency we can achieve with a cycle time of 5 minutes. The minimum number of workstations with that cycle time is 8, and then we have our constant of 39 minutes. All right, moving on to number 8. What impact would a 20% reduction in cycle time have on output? And we have to assume that the current cycle time is 5 minutes. So when we look at output, we go back to that formula that we talked about earlier in these in the exam here, that output equals our available time divided by our cycle time. And remembering that we've got 450 minutes of available time divided by a cycle time here of 5 minutes, so 450 divided by 5 leaves us with an output of 90. And actually our output is in 90 units per day, because we knew that 450 is the maximum number of available minutes per day, and our cycle time was in 5 minutes increments. So our output of 90 units with a 5-minute cycle time. So let's look at what a 20% reduction in cycle time has on that output of 90 units. So when we think about let's move forward, of a 5-minute cycle time and a 20% reduction, so we're going to take 5 times 0.2 equals 1. So a 1-minute reduction in cycle time would leave us with a 4-minute cycle time. And in our example equation here, we use output equals 450 minutes divided by our 4-minute cycle time. And that new output comes to 112.5 units per day. So with a 20% reduction in cycle time, we see that our output has increased to 112.5 units per day, or an increase of 22.5 units per day increase in output. But we didn't have a units per day increase in output available for our labels on the exam. We did have, however, some percentages that were available as a label. So if we look at our 22.5 units as being the increase, we take 22.5 and divide that by our original output of 90 equals 0.25 times 100 equals a 25% increase in output. So that's the answer we were looking for, is a 25% increase in output. So in looking at this, a 20% decrease in cycle time had a 25% increase in output. And finally, moving on to question number 9. What would it take to achieve 100% line efficiency? And note that your answer may require more than one numeric variable and descriptive labeling for each. So, line efficiency at 100%. 100% efficiency would equal the sum of our task times divided by the number of workstations times cycle time. So we know that 100% needs to equal 39 minutes, because that was our constant of our sum of our task times. 39 minutes divided by two components in our denominator, the number of workstations and our cycle time. So the only way to get 100% here would be to divide 39 by 39, which means two numbers times themselves here, times each other, needs to equal 39. So we go back to some of our high school math and know that we need to factor 39 into two different components. So we could look at 1 and 39, or we could look at 39 and 1, because 1 times 39 and 39 times 1 equals 39. However, neither of those numbers were available on our answer sheet. So we know we need to look at two other factors for 39. And let's keep in mind that our number of workstations needs to be a whole number, because we can't have fractions of a workstation. So we need two other whole numbers, or at least one other whole number, in factoring 39. And so if we look at 3 and 13, or 13 and 3, 13 times 3 does equal 39. So we could use either of these as cycle time and workstations. And our answer sheet did allow for us to pick them independently. We could look at 3 workstations and a cycle time of 13 minutes, or 13 workstations and a cycle time of 3 minutes. Either direction would have worked, and in picking both those numeric values and the descriptive labeling of cycle time and workstations, would accomplish a 100% line efficiency. Those were the only numbers available on our answer sheet that would have worked for the factors of 39. Now, it doesn't mean that we couldn't have used 2 and 19.5. That would have also come out to be 39, but I tried to stick with the more obvious factors for 39 and using the whole numbers of 3 and 13. So those were the numbers I was looking for and the answer to number 9. That concludes this depiction of our answers for the exam questions.